Hello, everybody. My mic on? Good evening. Can you hear me? My mic is on. Okay, good. Welcome to our 18th season that you've already heard about from Erica. I am John Mulchaey, for those of you who don't know. I'm the host of the series, and I'm also tonight's speaker, and I decided I would just introduce myself. It was easier than trying to get somebody else to do it, and that was my introduction. That's what you're going to hear. I do want to take this opportunity to remind everybody that we're doing something a little different this year. If you look at the calendar, we're doing one talk a month as opposed to every other week. And so the next talk here is March 23rd, and the tickets become available tomorrow at 10 a.m., so that's the important thing. So please be sure to go online and get your tickets for that talk. I want to take this opportunity to thank the Norris Foundation, which provides funding for this series, allows us to do it. I want to thank our friends here at the Huntington for hosting us, and I want to thank all the volunteers from Carnegie and the Huntington who helped with the check-in process and made it so smooth. And I want to thank you all for coming out. This is really exciting. So with that, I'm ready to go, I think. Whenever there's a new decade, it always gets people thinking about things in the past and what has been accomplished. And as we entered the 2020s, I started thinking about really what had happened 100 years earlier in the 1920s. And it turns out the 1920s were a particularly important time in astronomy. Really, it's during this decade that our modern view of the universe really emerged, thanks to astronomers like Edwin Hubble and others using the telescopes at Mount Wilson. And so that got me thinking, well, let's take a look back and see what we can learn from yesterday and, from looking back and forward. And if you look to 1920 itself, it turns out there was a really interesting event that's kind of in the folklore of astronomy. It's become known as the Great Debate. And the ironic thing about the Great Debate is it wasn't a debate at all. It wasn't a debate in the sense where you had two people presenting opposing views and actually interacting and giving rebuttals. It was, in fact, just two scientists got up and gave talks back to back with different visions of what the universe was like, but there really was no actual discussion between them. But it was still a very interesting and important and timely event. And so the issue was, what was the size and scale of the universe? And there were two camps here. One camp was led by Carnegie's Harlow Shapley, and Shapley believed that the universe really was composed of the Milky Way galaxy and not much more. And the reason Shapley believed this is because he had spent years, the previous few years, up at Mount Wilson, taking observations, measuring the size and scale of the Milky Way. And the scale he had found for the Milky Way seemed so large, he could not imagine that there was a universe bigger than that. So the Milky Way really had to be the whole universe in Harlow Shapley's mind. And there were other people who believed in that. The opposing view was held by Curtis, who was an astronomer at UC Santa Cruz. And Curtis had been studying these fuzzy things on the sky called nebula, spiral nebula, and there's an example right there. And Curtis looked at the light from those nebula and was convinced it was the light from many, many, many stars. And he thought that's what the Milky Way might look like if you could actually step outside of it and look at that light. And so Curtis believed what we called the island universes, that is, that these objects were separate from the Milky Way. Now, as I said, it wasn't really a debate, or much of a debate at all. Each one got up and presented their results. The papers at the time suggest that Curtis probably won the debate, at least in terms of his abilities. He was a very good speaker, much better than Shapley. But the real answer to the Great Debate was answered just a few years later, right here in Southern California, by Edwin Hubble. So it was only 1923, just 3 years later, Hubble took the observations at Mount Wilson that allowed him to measure the distance to that same nebula I showed you on the previous thing, which we now call the Andromeda Galaxy. And based on that, Hubble showed that, in fact, the Andromeda was very, very far away. And in fact, even the universe that Hubble found, Andromeda was about 5 times farther away than even Curtis believed. So even though some people believed the universe had more than one galaxy, it was much bigger than people realized. It's quite ironic that Harlow Shapley, who of course didn't believe in anything beyond the Milky Way, was the one who ended up naming these objects galaxies. And in fact, Hubble himself didn't like the term galaxies. Galaxies comes from the Greek word milk, and so it refers to really the Milky Way. When we refer to the galaxy, we're referring to the Milky Way. And Hubble preferred that. He was a very sophisticated gentleman, and so he thought that galaxies just didn't apply. Anyhow, this great debate, that wasn't really a debate at all, happened and just a few years later was solved. And so this got me thinking, 100 years later, what are the great debates today? And so over the last 2 months, I've sat down to try to think of what are those great debates today? What are the questions that we really don't understand? And unfortunately, I came to the conclusion that there really are none. And this isn't strictly true. But what I'll say is that there are none in the way the Great Debate. The Great Debate had two different camps with a lot of people in both camps who had very different and bimodal ideas of the universe. They were quite extreme and quite different. And if you look at astronomy today, there are very few things where you would, for instance, have half the population, half the astronomers believing one thing and half believing the other, as was probably the case back then. That doesn't mean that there's not some disagreements, but it just turns out that there's a lot more consensus in astronomy than there has been in the past. And I think that by itself is rather interesting. I've thought about that. Is this just an indication that we actually understand the universe better in 2020 than we did in 1920? Or is it actually a result of the fact the way astronomers work? In 1920, Edwin Hubble would have been sitting in his office working on his own, coming up with his own theories, as was Shapley and all these individuals. In that environment, it's quite easy to kind of come up with your own theory and kind of be very attached to it. Where today, we actually work in very large collaborations around the world, and information is very freely exchanged. And so maybe the fact that there's more consensus today is just an indication of the way we work. So my talk could be over here because there are no great debates. But there are some really fascinating topics. And so instead of talking about the great debates, I'm going to talk about what are the things that we really don't understand. What are the big questions for today? And I thought I would start with the most recent of these mysteries in astronomy, and these are really fascinating. And in fact, you have to read the news every day, literally every day, because there was a news story about this yesterday, on a topic called fast radio bursts. Now, I don't know how many of you have heard about the fast radio bursts. These are really interesting. These are energetic bursts of radio emission that occur. They last about 1,000th of a second, so extremely short, but appears to have a lot of energy. And the interesting thing, they were first found in 2007, which is pretty recent by astronomy standards, and they were not found in real time, or they were observed, but they actually were found by people looking at old data. Astronomers were going through old radio data taken with the Parkes radio telescope, and they noticed that these events had occurred. And there you see in the image there, you see like 4 blips. Those are 4 different cases of fast radio bursts. And so when these were announced in 2007, I think a lot of people didn't really pay much attention. They were interesting, but what were they? But over the few years after that, people started going, well, maybe these are something we should actually be paying attention to. Well, we finally caught a fast radio burst live in 2014. And so here you see, this is the Parkes radio telescope, which is the same one that had found the original ones in the old data. You see that little blip there on the up. That blip is the fast radio burst, a burst of radio emission. Now, when this happened, astronomers in Australia found this, and some of us were fortunate enough, including myself, to be at telescopes around the world. I was at the Magellan telescopes, which are Carnegie's Las Campanas telescopes here. And so I got a call from a colleague saying, will you point the telescope at a region of the sky and see if you see anything with your optical telescopes or visible light that might correspond to this fast radio burst? And I did, and I saw nothing. And sometimes nothing's okay, but in this case, it wasn't very exciting. It wasn't very satisfying. But this was a big accomplishment because we had seen one of these in real time. And so we knew that this was kind of fun. But at that point, all the fast radio bursts that had been seen, in fact, were all seen from the same telescope. And so this is always something you're a little worried if you only see something from one telescope. And so this was kind of a laundry list of the possible origins for these radio emissions that we would have had, say, in 2014. And the first one there on the left is a telescope artifact. And that is a picture of some radio telescopes and a microwave. And that is very intentional because some of you may know this story. This same Parkes radio telescope had seen another interference, we'll call it interference, a mysterious signal that had been going on for about 20 years. They kept seeing these signals. And it turned out it was only solved a few years ago. It actually was the microwave that the astronomers would use at the observatory. And they finally figured this out. It makes it sound really smart. They figured this out by actually realizing the pointing of the telescope was related to the direction of the microwave, and that it only happened during the day when the astronomers would be eating. And so, literally, you think I'm joking. Look it up on Wikipedia. It's actually true. Anyhow, so whenever you see something, even in 2014, when you've only seen it from one telescope, you have to be worried it's a problem with the telescope. So telescope artifacts are one. We also know, of course, that radio emission is used for communication around the Earth, and so whenever you see something like a burst of radio emission, you have to be worried it's something related to the Earth, terrestrial phenomenon. And then we, of course, have more interesting things. Exploding stars, that's of course something that happens and is very quick and you could imagine be associated with something like a radio burst. Black holes and neutron stars are very, very dense objects, and so we know that it's possible to get very high energy events around them. And you can never, of course, rule out aliens. Unfortunately, we try, but people love to talk about the aliens, particularly when it's a radio emission, of course, because that's how we communicate, so a lot of people like to believe in the aliens. Anyhow, we've made a lot of progress in understanding these possible origins in the last 5 years, and this is really quite impressive to me. One, we actually can rule out the telescope artifacts, because these fast radio bursts, unlike that other class of microwave object, these have actually been seen from multiple telescopes now. It was very soon after the original ones were seen with Parkes that Arecibo and Puerto Rico saw them, and we now see them from many ones. So they do appear to be real things. You can also rule out the terrestrial models, because by studying the property of the radio, we can show that the radio waves have come from very far away. And so, in fact, they couldn't really originate here on Earth. And so those are the boring ones, and we're happy to get rid of those. Now, a really interesting result happened a few years ago, where somebody, once again, using these telescopes, had gone and seen a fast radio burst that repeated. That is, prior to that, they had only been seen once. So these blips had happened, and we never saw another one from that region of the sky. But then one was found that actually repeats. And this is interesting, because if you think of something that repeats, it's unlikely it's associated with something that happens once, like an exploding star. And so this seems to rule out that these fast radio bursts are related to exploding stars. I will point out, because I know you all remember, I gave a talk in one of these talks in 2015. I actually talked about fast radio bursts in that talk. And I said I believed they likely were due to exploding stars. So I'm the first to admit right here that I was wrong. But the fact that you see these repeating seems to eliminate that as an option. Okay, then the last year has been really exciting in this field, because as the telescope, we've used different radio telescopes to actually pinpoint the location of the fast radio bursts on the sky. The Parkes radio telescope really didn't have good resolution, so it's hard to figure out where the light was coming from, the radio was coming from. We now have actually measured 2 fast radio bursts to be associated with distant galaxies. And you can see it's a tiny little galaxy, in this case, 3.6 billion light years away. And this one here is part of this galaxy here, about 500 million light years away. Now, what's interesting about this observation is this tells us that these are coming from very, very far away. And what that means is you can calculate the energy that's coming from these fast radio bursts, and it's a huge amount of energy. Even though these bursts last 1,000th of a second, they're producing about the equivalent of almost 100 times the energy of the sun, the energy of the sun over 100 years. So if you took that, that's a lot of energy coming out in 1,000th of a second. These are really tremendous objects. And so going back to our list of possibilities, we've ruled out a lot of the more boring ones, and some other ones like exploding stars. But these are kind of the current ones that most astronomers believe in. Well, I should say, I know most astronomers believe in, but these are the likely ones. And so we still have the black holes and neutron stars. Once again, these are dense objects where we think you can create high energy phenomena pretty easily. And of course, you always still have the aliens. I would point out, though, however, for me, as soon as I realized how far away these things were, that to me kind of rules out the aliens as a likely scenario. Because if you think of that, I said, these events are basically the equivalent of the sun for 100 years. That's a lot of energy, and it's really hard to imagine the aliens could do that, but who knows. But a really interesting result happened in the last 2 weeks. And we've seen another one of these fast repeating bursts. So this burst is happening over and over again, but this one actually happens in a very regular way. It happens over a 16-day cycle. Basically what happens is this thing you get a burst, a couple an hour for 4 days, and then you see nothing for 12 days, and then it comes back in the same pattern. So it's a very repeatable pattern. And this is really interesting. And so what most likely this is, to me, is this most likely means we're looking at some sort of binary star system, where the actual radio burst may be coming from say a neutron star or some high energy thing, but this neutron star and this other star are kind of whipping around each other over a long period of time. And so for 4 days, for instance, the neutron star might be pointing at you in some regular way where you see the blips. And then as it revolves around, it may point away from the Earth and you don't see it. This is really new result. This paper hasn't even actually been accepted yet for publication, but it's been all over the news. I do want to point out, this is why I say you have to pay attention, because if you look at the news, and you do fast radio bursts in the news over the last day, There's a whole bunch of stories about how this is aliens. And unfortunately, this is because there's a professor, Avi Loeb, who many of you will be familiar with at Harvard, who loves aliens. He's actually a really super smart guy, but he was the one who had the space rock, Oumuamua. Many of you know I've talked about this a lot, that he was this strange space rock that a few years ago came through the solar system, and he was convinced was aliens. And now he said yesterday, we can't rule out aliens here. Well, we certainly can't rule out aliens here. But once again, I think the energies are hard to imagine. But if you're a Harvard professor and you say aliens, you get a lot of attention. And that's where we're at with the fast radio bursts. So where are we at? So this is a field that only started in 2007, and I think we're very rapidly starting to see lots of new observations. There's this amazing new telescope called the CHIME telescope, which is the one where a lot of these fast radio bursts are being found. And this system is finding them at such a huge rate that I think over the next few years we're really going to figure out what these things are. And so while this is the newest mystery in astronomy, I think it's one that actually could be solved pretty easily. Now, unfortunately, that doesn't apply to the next one, which every time I talk about dark matter, I get in trouble, and I'm certainly going to get in trouble again. We just talked about a mystery that's been around maybe not even 15 years, and that is quickly coming to a resolution. Dark matter is really the biggest outstanding problem in astronomy in some sense. And it's been around since at least 1933, at least that's where I would date it to, which is the work of another, this time a Caltech professor, Fritz Zwicky. And so this is a problem we've had for 90 years, and as I'll describe now, we still have a lot of real questions. So let me just talk a little bit about why do we believe there's dark matter, and I think most astronomers believe there's dark matter. And the way we do this is really by just watching the motions of things. In the case of Zwicky, he was studying these rich clusters of galaxies, and this is a picture of the Coma clusters of galaxies. What you see here, basically all these little fuzzy things that are kind of all yellow, are all galaxies that are part of a single system. These galaxies are all kind of moving around, and that their velocities are dependent on the gravity they feel. And so what Zwicky was doing is he was measuring how fast these galaxies were moving. And what he realized was that, in fact, they were moving way too fast for the amount of material you see in the stars. And so what he implied was, in fact, there had to be an additional dark component that you just were missing. And this component he called dark matter. And so the field was born really in 1933 with this observation. Now, that's, of course, not the end of the dark matter story. Although for the next few decades, there was very little work on this topic, it was really Carnegie astronomer Vera Rubin and Kent Ford that really were responsible for kind of bringing dark matter to the forefront as a problem in astronomy. And what Vera and Kent were doing was they were studying individual galaxies at this time. They were studying the motions of stars in the outer regions of galaxies. And what they found was rather surprising. And you can see it plotted here. So this is just velocity going up on the y versus distance from the center of a galaxy. And you see the green curve here shows you the velocities. What they found is that as you moved farther out in a galaxy, the stars were actually moving faster than the stars at the middle. And does that make sense? Well, it doesn't make sense in some sense because if you look at a galaxy, you see that most of the stars appear to be near the middle. So if the stars were the only component of gravity, you would expect that, in fact, the curve would do more like, you can see that dash curve there. Let me just show you, this is a great example. I love considering the solar system here because this really explains it. In the case of the solar system, we know that 99.9% of the mass is at the middle in the sun. And so what happens in the case of the solar system is the farther you move away from the sun, these are the planets with Pluto, as the farther you move away, you see the velocities decrease. In other words, Pluto travels much slower than the Earth because it's much further from the center where all the mass is. But this is not what happens in galaxies. This is what we thought might have happened in galaxies would be that yellow line, but in fact the velocities go up. This implies that most of the mass in a galaxy like the Milky Way is in the outer regions. And in fact, if you look at this very closely, you can extend these studies further by going into with radio observations. Most of the mass is well beyond where you even see the stars. And so this became the real dark matter problem in galaxies. And it was Vera Rubin and Kent Ford's paper in 1980 when they showed this effect was generic for pretty much all spiral galaxies that really caused dark matter to kind of move to the forefront. And astronomers went, wow, this is a problem. So this is the 40-year anniversary of that important paper. But there's, of course, more observations that are consistent with dark matter. Going back to clusters of galaxies, this is a beautiful cluster of galaxies here. Once again, you see all the yellow things are galaxies in an individual system. moving around very rapidly. What I plotted on top of this is the purple here is an X-ray image. And X-rays are very good, X-ray telescopes are very good at seeing hot gas. And so what you're seeing here is that the galaxy cluster, in addition to the galaxies, is contained in a sea of hot gas. And the question is, why does this gas exist? If you have a hot gas, that means the particles are moving around very rapidly. And if you just left that in space, what you would expect is that it would quickly dissipate. And so a gas cloud like that shouldn't actually exist unless something is containing it or keeping it in. And that, once again, is what we believe is the dark matter. In this process we call this process hydrostatic equilibrium. This is a case of it in the sun. In the case of the sun, gravity wants to scrunch the sun down, the mass of the sun, but then the sun has nuclear diffusion in the center, producing gas pressure that's expanding outward. And the two have reached a perfect balance, which is why the sun is stable and steady. And the same thing with these X-ray clusters. These gas clouds are seen in every cluster, and they're always very stable and existing. You can use the temperature of the gas to imply how much stuff is there. And when you do that, you once again imply that most of the material you just don't see. Once again, you need the dark matter. And by the way, if you look at the velocities of the galaxies and the temperature of the gas, those two numbers give you the same amount of value. Once again, giving us some idea that we think we're doing the right thing. And then finally, there's what's known as gravitational lensing. And this is really kind of fun. This comes out of Einstein's theory of general relativity. If you have a massive object, imagine this is, in this case, a cluster of galaxies, and you have a telescope over here. If you have an object behind it, the gravity from the cluster, the foreground cluster, can actually bend that light. It acts like a lens. And you can use this lens, you can see these lenses, you can sometimes produce from the telescope, you'll see multiple images. And these are really quite spectacular. These are some examples here. So here you see these four images are all the same object that has just been lensed by a foreground dark object, or darker object. And you see, it depends on the geometry. In some cases, they're off here, but these four, for instance, are all part of a lens. And sometimes, if you're really lucky, you get these beautiful arcs like this. And so we see this lensing, but you can use the lens, you can model it, and work your way backwards to figure out how much mass do you need to produce this lens effect. And when you do that again, you require the dark matter. So basically, all of these observations I just talked about, from individual galaxies to gas-in clusters to this lensing, all seem to require the presence of this dark component we call dark matter. And I didn't talk about some other ones, but including the cosmic microwave background. This is the remnant radiation from the Big Bang. Modeling of that seems to imply dark matter as well. And it turns out we have a hard time making galaxies. If you do simulations of how you make galaxies, it's almost impossible to do that without a dark matter component. So, why am I worried? It looks like this is pretty convincing, right? The problem is when you go to look for the dark matter, we have a really hard time figuring out what it really is. And there's several classes of dark matter. The first that have been proposed, the first is what we call baryonic dark matter. That just means it's made of objects like protons and neutrons. And one option is to say, well, maybe the universe is filled with dark astronomical objects. And so these are some examples here. Neutron stars, black holes. My favorite are the black dwarfs. Many of you haven't heard about a black dwarf, so I'll tell you about what a black dwarf is. When a star like the sun dies, it kicks off its outer layer and leaves behind a hot core, which we call a white dwarf. And that white dwarf will lose energy over time, and eventually, after enough time, it will become a black dwarf. In other words, it'll be basically a mass that doesn't shine anymore. And so that's what a black dwarf is. So you can imagine if there were lots of those, they could be the dark matter. A brown dwarf is a star that never was a star. It's a failed star. So it just never got enough energy. It was not big enough and massive enough to have nuclear fusion and shine. So they, once again, are not very luminous. And then, of course, we know planets, for the most part, don't produce their own energy either. So you can imagine you have a bunch of planets. So these all would seem like logical choices, and for a long time, astronomers were looking at all of these. By the way, this class was called MACHOs, which stands for Massive Astrophysical Compact Halo Object. In other words, the idea is big, massive objects, astronomy objects. But unfortunately, observations over the last several decades have really ruled out all of these as possibilities for the dark matter. And there's various reasons. Some of them, like neutron stars and black holes, it's hard to understand how you could create enough of them, honestly. Black dwarfs, we, by the way, don't think even exist. Because to get a black dwarf, you need a white dwarf that cools for tens of billions of years, and the universe is only 13.7 billion years old. So we don't think black dwarfs exist yet. And we know numbers of brown dwarfs and planets, and they just don't seem to add up. But more importantly, all of these can really be ruled out by this gravitational lensing I talked about. Because if you imagine our Milky Way galaxy, we're sitting at the middle of the Milky, or at the edge of the disk of the Milky Way, we're surrounded by a halo of dark matter. But if that dark matter was made of these very massive objects, light from distant objects would actually have a gravitational effect. You might see what we call microlensing. And we've looked for this microlensing, and we don't really see it in enough numbers to explain this. And so basically, all these astronomical versions have pretty much been eliminated. So that leaves things that make physicists more exciting, maybe not the astronomers as excited, called non-baryonic. And these four here are kind of the ones that get the most attention. These are all different types of particles that we don't really know very much about. In fact, in three of them, in the case of the axions, the WIMPs, and the SIMPs, these objects here are all theoretical, let's go with that word, are theoretical particles that have been suggested, and they help solve the dark matter problem, but we really have no evidence of their existence. In the case of the neutrinos, this is a small particle that we do know exists, and we can see neutrinos, but the three types that we see don't have enough mass and don't have enough number to actually explain the dark matter. And so basically, these other three, there's a lot of experiments going on by physicists here on Earth trying to understand if they can detect these things, and sadly, none of them have been found. And this is becoming a little bit troubling, because I think most of us, in fact, the WIMPs were really the favorite, but the recent experiments haven't been able to find these WIMPs, and so I think people are getting a little bit concerned that we haven't found them yet. I'll just mention one down here at the bottom, primordial black holes, because I love this. This became very popular for about 2 years and then got quickly eliminated. But the black holes I talked about earlier were really formed from stars that died, but it turns out in the first second of the Big Bang, you could produce a lot of little black holes called primordial black holes, and those may have grown over time. But once again, the lensing experiments seem to kind of rule out those as well. So what I've shown you is that we believe there's good evidence for the dark matter, but we can't find any of it. And so that's a little bit of a problem. So this has led a minority of astronomers, this is the closest to a debate as you might get, to think that maybe we have something entirely wrong here. Maybe dark matter doesn't exist at all. And in fact, maybe our understanding of gravity is just wrong. And so people have been trying to model, do new models of gravity called modified gravity, where what they basically do, we know gravity works really well on the scales of, for instance, the solar system. We can do all sorts of experiments. General relativity is really quite brilliant over those scales. But what if on very, very large scales, the scales of galaxies or the scales of clusters of galaxies, gravity worked in a different way? And so these things are called modified gravity. Now, I think it's pretty intriguing, and there are people who really work on this and believe in this quite a bit. The challenge has been modified gravity models often work in one realm but not another. So as an example, there's a really good class of modified gravity models called MOND, which describe the rotation curves of galaxies, the Vera-Rubin result, really, really well. But unfortunately, when you try to apply them to the big clusters of galaxies, they don't work so well. And this is generally the problem with most of the modified gravity models. And then furthermore, I can never give a talk anymore without talking about the exciting 2017 neutron-neutron star merger. Because it turns out this particular event, which many of you know because it was based largely here in Southern California, really is a problem for most of the modified gravity models. General relativity predicts that gravitational waves, and electromagnetic light should both travel at the speed of light. And so in 2017, the neutron-neutron star merger was seen by our colleagues at Caltech and MIT with LIGO. And as many of you know, we saw the light was also detected from this event. Here, this was our detection in optical light at Las Campanas Observatory, but it was also seen in in gamma rays almost instantaneously with the gravity waves. So this prediction, this observation, the fact that we saw the gravity waves and the light waves at the same time is exactly what general relativity predicts. However, if you try to modify general relativity to explain the dark matter, you get a lag between these two components. And in fact, most of the models would predict that you should have seen the gravity waves hundreds of days later than you saw the light. And so with this observation, to me, has really eliminated the vast majority of those models. And so this leaves us with a very unsatisfying part of the talk. When I worked on this talk, I'm like, I don't know if I should just throw this out. But I felt, because it's really rather frustrating. We have many astronomical observations that are consistent with the dark matter. I think this is why most astronomers, I would say 99% of astronomers will tell you they believe in dark matter. Alternative gravitational models is an interesting alternative, but they have all these other problems. And this recent neutron-neutron star merger is a real problem for many of them. So it doesn't mean that there aren't better models out there, but so far none of the models work in a way that I would consider very satisfying. Yet at the same time, we can't find the dark matter. And that's becoming very frustrating. And so this is the point, somebody asked me this once recently, if there was something about the universe that you think astronomers have really, really wrong, what would it be? And I wouldn't say, well, I am being streamed live, so I have to be careful. And there's a lot of astronomers in the audience. I wouldn't say that I don't believe in dark matter, but I do wonder if we're getting to the point where if these dark matter searches don't find the candidates, are we really missing something in a real big and fundamental way? And in fact, every time I give a talk and mention dark matter, somebody gets up and says, oh, it doesn't make sense. Why do you believe in that? But I think there's good reasons to believe in it, as you saw. But it is very troubling that in 2020, after 90 years, we still haven't figured out what this is. So that's the dark matter component. So now on to funner things. One of the things Edwin Hubble did, besides after he had, of course, measured the distance to Andromeda, about 5 years later on, he went to basically find the evidence that suggested the universe was expanding. What Edwin Hubble did is he basically plotted the distances of galaxies versus how fast they were moving away from us. And what he found was there's a very interesting relationship where the objects the furthest away from us are traveling fastest away from us. And this observation is consistent with an expanding universe. This is not, by the way, Edwin Hubble himself never said that. And he used a lot, and this plot particularly involves some of the data was taken from other people. But he was the first to kind of put the two plots together. And Hubble, I think, was very uncomfortable with the idea of an expanding universe because it is a very uncomfortable thought. But I just wanted to show, we call this diagram the Hubble diagram based after this work. I just wanted to show you, this is a more modern version of the Hubble diagram, where Hubble's point is basically that first point there. And so just to show you how incredible over the last 100 years or so, we really have expanded these measurements to much, much more distant objects. But as many of you know, when you look at this very closely, in the late 1990s, a very exciting result was found, and that's that the things didn't fall the way you would think they would. And so if you follow here plot, these are measurements of more distant galaxies here. If you look what the red line is, this is what would happen if the universe was expanding at a steady rate. And what you could see is that the data points clearly don't follow the red line. They clearly fall above it. And this is consistent with objects that were moving, that the universe was expanding at a slower rate in the past. Or to put that another way, the universe is actually speeding up. The universe is accelerating. And so, of course, this was announced in 1998. I would say that many of us were very skeptical at first, but two different teams have found the same sort of result, and there have been other observations since that are consistent with this result. And this, of course, led to a Nobel Prize. And so this is really quite interesting. Why is the universe accelerating? And so we blame this acceleration on a force we call the dark energy. And you can see we're going down the same kind of path we went with the dark matter here. Dark energy is an unknown form of energy that counteracts gravity and is causing the universe to accelerate. And so once again, the term dark, we keep getting ourselves in trouble here. I'll just leave it at that. And so what is the dark energy? What is this force that is making the universe accelerate? Well, there are many solutions being proposed. This is a relatively new field. It's only 20-something years old, unlike the dark matter problem. And there are many different types of solutions, but the main ones fall into kind of two categories I would call here. The main one that I'd say most people believe is what we call the cosmological constant. This is just the idea that space itself has an energy associated with it. We call it vacuum energy. And this cosmological constant actually was in Einstein's original equations for general relativity. Now, he had added this into the equations to keep the universe from expanding or contracting. Einstein believed the universe was static, that is, it was the same size. But his equations seemed to imply that it either was expanding or contracting. And so he had to add a force in to kind of keep it static. And that's what he called the cosmological constant. Now, he threw out that equation, he threw out that term when he saw Edwin Hubble's results. He realized very quickly that meant the universe was expanding and that he didn't need the cosmological constant. But now that the universe is actually accelerating, it seems that perhaps it's needed. And the second form is called quintessence, and I'll show you a little bit about that. This is a case where it's not a constant energy to space, but that it can actually dynamic, it can change in time. And this really depends, the nature of the dark energy, will really tell us where the universe will end up. If you believe the cosmological constant, which is what most people would favor, you get a universe that continues to expand forever, and eventually what will happen is that you won't even see galaxies. The nearest galaxies will have expanded away from us. But it's still kind of a very peaceful existence. We'll just kind of expand forever. But with quintessence, you can actually do all sorts of weird things. You can, for instance, assume the dark energy changes direction or changes, so it's no longer anti-gravity, but it actually works towards gravity. And in that case, the universe can come crashing back down on itself in what we call the big crunch. And you'll know that there's some people who believe the universe is accelerated between big crunches and big bangs. Or you can do the opposite extreme, which is the dark energy just becomes much more powerful over time, and the universe basically can't even hold itself together. Atoms are ripped apart in what we call the big rip. And so these are the various scenarios. Now I'll say that almost all observations at the moment are consistent with the cosmological constant. And the nice thing about the cosmological constant is that this really fits in very well with Einstein's theory of relativity. And so I would say that most people would believe this is kind of where we're headed. But the reality is we can't really rule these other things out until we understand dark energy better. And so that's something that will happen over the next decade. And so what I would say in terms of the fate of the universe, at least in 2020, and I should say that if you asked me in 1994 when I was a graduate student, it would have been probably different. But right now, in 2020, we believe the universe is likely to expand forever. But we really need to understand dark energy better to know. Okay, and so my last big debate question, or question of all, is really kind of the most interesting in some sense, and the one with absolutely no data, or virtually no data. And this is the question of, are we alone in the Milky Way galaxy? And I decided to concentrate on the Milky Way galaxy as opposed to the entire universe. Some of you know I give a talk, Search for Life in the Universe, and when you consider the whole universe, it's really big. I figured, why not just concentrate on our own little neighborhood, the Milky Way? Because if we're ever going to communicate with aliens, they almost certainly would be in the Milky Way. I think going beyond that would really be impossible. And the reason I threw this in here was because I went to a really interesting talk given at the Breakthrough Initiative called the Breakthrough Initiative up in Palo Alto about 4 years ago now, where there were about 200 astronomers in the room who work on searches for life and studying other planets and things of that sort. And they did a survey at the beginning. I got invited because I was a director of an observatory and they were interested in using our telescopes, I think. I have nothing to do with that science, but they figured, why not? And so we asked the 200 astronomers at the beginning, do you believe there's life elsewhere in the Milky Way? And all 200 people said yes. Then they asked the second question, which is, do you believe there's intelligent life elsewhere in the universe? And there wasn't a consensus. About 25% of the people in the audience said no. And it was really quite interesting. So why did that 25% not believe, or believe we were the only intelligent life at this moment in the Milky Way galaxy? I should be careful with this moment. And there were two reasons. One, some of these individuals were convinced that if there was intelligent life elsewhere in the Milky Way, we would have heard from them by now. I'll describe in a minute why I think that's not really necessarily true. But the second argument was a little more dismal argument. And they realized that here on Earth, we've had technology to communicate for about 100 years. And over that 100 years, we've also developed all the technology to kill ourselves off. And so they thought that quite likely what happens is as civilizations develop and they become very smart and technically advanced, they soon extinguish themselves. And so in their mind, if an intelligent species only lasts 100 or 200 or 300 years, that quite likely the odds of there being another one at this moment in time were very slim. That's pretty dismal. I would like to think, at least that if they're really intelligent, they actually figure out how to solve the problems that they've created. And that's what we'll try for. Anyhow, it was really quite interesting because what this says is that there really is a debate in some sense about this question. And so let's just take a little quick look and say, well, should we expect life here in the Milky Way elsewhere? And if we should we expect to hear from it? And so there's, of course, been a lot of great work recently studying planets around other stars in our Milky Way. This is really fascinating. As of today, there's over 4,000 planets known around other stars. It's not just the 9 or 8 that you grew up with in the solar system when you were a kid. We now know of over 4,000. But the remarkable thing is that most of our detection techniques are really limited to a very small region. They're just really hard to find these planets. And so if this is a drawing of kind of the Milky Way, you can kind of see this is the region over which most of those 4,000 planets have been found. We are really only exploring our local neighborhood, at least in real depth. But you can extrapolate the results from that little region to the whole galaxy. And if you do that, we know that there's about 200 billion stars in the Milky Way. And if we assume that each star has about 5 planets, which is probably not a bad assumption based on those observations and the fact that our own solar system has 8 or 9 planets. So if you say 5 on average, and you multiply that together, you get about 1 trillion planets in just the Milky Way alone. That's a big number. And it's that number here that's why everybody in that room said they thought there was probably life elsewhere in the Milky Way. Because that's a lot of opportunities for life. So that's pretty interesting. So then you have to ask the question, well, then why haven't we seen life elsewhere in the universe? This is my favorite slide. The internet's a wonderful thing sometimes. And so if life is so common, why have we not heard from the aliens? Well, it's interesting. If you think about how there are people who, of course, spend their careers searching for actual signals from extraterrestrial life. This is called SETI, as many of you will know, and there are others working on it. But how do they search, and what do they search on? The interesting thing is if you look at SETI, what SETI is looking for are signals very like the signals we send out. It's based on the limited one place we know of in the universe, which is us. And if you look at the radio signals from Earth, we've been sending out radio signals for about 110 years here on Earth. That's a pretty long time. And since radio signals travel the speed of light, this means those radio waves have propagated out 110 light years around us. That's a pretty big volume, right? In the case of I Love Lucy is coming up on its 70-year anniversary. Those I Love Lucy signals have now gone out 70 light years, right? So there could be aliens within 70 light years looking at I Love Lucy. That's what that figure means. That's what that came from. So what does this mean, actually? Well, it's really quite interesting. If you look at it here on the right, you see this is a distribution. You probably can't see the scale there very well. This is about out to a radius of about 100 light years. These are all the known stars within that 100 light year radius. It's a decent number of stars. And remember, if each one of them has a few planets, that's a lot of planets. So in theory, our signals have gone out very far. But this is the plot I really love here, and this is maybe almost impossible even to see. This volume here, where we have actually communicated outward, in some sense corresponds to that little blue dot. I don't know if you can even see it. And that little blue dot is from this square, which is just this square here. So in other words, it's not even that a single little dot on the Milky Way. The Milky Way and the universe is so immensely huge that even something like 100 light years, which seems like a very long distance to humans, is really just the tip of the iceberg. And to me, this explains one reason why we don't hear from a lot of aliens. Because the Milky Way is just so incredibly large that those distances are really hard to cover. And so you'd really have to know what you're doing to try to find us. And more than that, we now know, as I showed you, there's 1 trillion planets in the Milky Way. And so if you were an alien and you wanted to find Earth, you'd have to really pick it. We'd have to be 1 out of 1 trillion. But maybe we are. So there's a further problem, and this is called the inverse square law. And this is just a law which tells you how light propagates. And as light propagates out, it diminishes its strength in a very fast way to the second power. And so if as a light signal moves out by a factor of 2, it's gone down by a factor of 2 squared or 4. If you go out a factor of 3, it's 3 squared or 9. So very quickly, those I Love Lucy signals are being diluted. And so in fact, if you do the calculation, what you find is that the signals, which were not very strong in the first place, in fact, probably would not even be detectable outside of the solar system. So in fact, if you take that at face value, we should not have heard from the aliens, or at least we shouldn't have expected the aliens, if they exist, to have seen our TV and radio signals and corresponded back. So this is interesting because this has been understood by the SETI folks really over the last decade. And so although they've been looking for kind of random radio waves from other aliens, they've realized that that's unlikely to happen if their signals are like our signals. And so instead, the new focus is maybe we can find a signal that's beamed at us, like for instance, a laser. There's a lot of fascination now with lasers. if an alien civilization had a laser pinpointed at us, then maybe we'd have a chance of seeing it. The other part of this conference that was really fascinating was then there was a whole discussion about if a laser was seen coming from another exoplanet at us, what do you do? Do you respond? Do you want them to know we're here? What if they come and eat you? And I'm serious that there are actual people who spend their time thinking about this. Anyhow, my point for this part was really just to say that I don't think we should be worried we haven't heard from people. The Milky Way is immense. There's a lot of planets in it, and the signals, at least that we send, are very weak. So unless something is focused at us, we really shouldn't expect to hear from them. But does that mean we can't find evidence for life elsewhere in the universe? And of course the answer is no. And this I'm much more optimistic about. And one thing you can do is you can just ask the question, if you studied the Earth from a distance, could you indicate that there might be life here on Earth? And the answer is probably yes or maybe. And the way we do this is you just look at the Earth and the Earth's atmosphere, because life on Earth has impacted what the Earth's atmosphere looks like. The original Earth's atmosphere, we think, was all volcanic. It was mostly carbon dioxide and water. And so, in fact, it was only in the last billion years or so when, in fact, oxygen has become a dominant or a significant component here in the atmosphere. This plot's a little complicated. But this is just showing time from the beginning of the Earth to now. And what you see is this is the fraction of oxygen in our atmosphere. What you see here is over the last billion years, there's this huge increase in oxygen in our atmosphere. This is caused by the plants here on Earth. And so, if you could take a look at our atmosphere and you saw an atmosphere that had oxygen in it, you might have some confidence that it could be a life-bearing planet. And the way you can do this is actually a spectrum of the Earth's atmosphere. It's really quite interesting. Many of you are familiar with spectroscopy. For those of you who are not, you know the concept kind of at a very basic level at least. If you have a prism and you put light into it, the prism, of course, basically breaks the light up into its multiple color components, different energies. Spectroscopy is doing the same thing, just at a much fancier level. And what you're seeing here is these wiggles here, this is the actual spectrum of the Earth's atmosphere. And these big dips you're seeing here are caused by the molecules in our atmosphere are absorbing that light, taking that light away. But what you can see from this is that there's all sorts of important things. You see water vapor, but you also see oxygen and ozone. There's actually some features in the spectrum which has to do with the presence of plant life on the surface, actually. This is really interesting. This means if you studied the Earth from a distance and knew how to interpret it, you could imply that there was actually life here on Earth without actually going to the Earth. And so our hope is that we can actually take data like this on planets around other stars and imply the presence of life. And those experiments are going on, but they're very, very difficult. Very, very difficult. And so, in fact, likely, I think, that our next generation telescopes, which are much bigger, are going to be needed to really do this accurately. But I'm fairly optimistic that at least in the next few decades, we will actually study many planets this way and hopefully find some evidence or potential evidence of life. But you may not need to go so far as going out to other planetary systems, because we now think that there's a lot of places in the solar system that are at least worth looking for evidence of life. And once again, in these cases, none of this is going to be walking, talking aliens, the kind you'd really want to find maybe. But the fact is, if you saw life in any form, even in the solar system, it would tell you that life must be very common, because it's happened on Earth and it happened somewhere else in our solar system. That would suggest that it is very common. So, of course, you're all familiar with Mars, which has always been a favorite for life. And there's reasons for this. Mars, of course, has a little bit of an atmosphere. It has liquid water on the surface. The temperatures aren't so bad. And you know, of course, many efforts by our colleagues at JPL are, in fact, still studying Mars as a potential life source. But these guys here have become really the more interesting ones in the last decade or two. These are the 2 moons of Jupiter and a moon of Saturn here. These 3 moons have liquid oceans. And the liquid oceans are likely water, or at least a significant component of water. They don't look like oceans because they're covered in ice. And so basically you have an ocean underneath and you have an ice surface. Well, how do we know this? Well, we know this because you can see it from spacecraft. These are some geysers coming out. You can see these beautiful things coming here. This is from Cassini, once again, our colleagues at JPL. These are some beautiful geysers. Here's some older data from the Galileo mission. And once again, you see these geysers coming out. This is direct evidence of liquids below these ice surfaces. And so our hope is that in the next few decades, it'll probably be several decades at least, one would be able to potentially send a mission to actually even sample maybe sample that and figure out if there's some primitive life form in these moons. And we don't know. I mean, that's obviously a pretty big accomplishment, but it would be really quite exciting. I should mention that Titan is really interesting. Titan is the biggest moon of Saturn. And as many of you will know, or some of you will know, Titan has a very thick atmosphere. Its atmosphere is actually thicker than the Earth's atmosphere. It also appears to have liquid lakes. There's some evidence of methane, some evidence of water. It, in many ways, looks like an early Earth. And so this is a really quite fascinating option here. And I threw Venus on because I was kind of surprised myself that people actually talk about Venus. Venus is very hot, as many of you know, on the surface. But it turns out that the upper layers in Venus actually stay a pretty temperate value. And so there are some individuals, and I'd say this is pretty unlikely, but that believe that you could have a life form existing in the atmosphere of Venus. But any of these, all of these will be explored, maybe not Venus, but the others will certainly be explored here in the coming decades. And if you found life in any of these places, it would really help us believe that life was very, very common. And so what I'll say about the life portion is, well, I think it's unlikely we will know in our lifetimes, most of us, whether there's intelligent life elsewhere in our Milky Way. I think that there's a decent chance we'll know whether there's life elsewhere. And if you see that life, to me that implies quite likely that maybe intelligent life does exist elsewhere. And so the 2020s are coming. You're going to hear in the next 3 lectures about some of these great facilities. The James Webb Space Telescope is the next follow-up to the Hubble Space Telescope. This is being launched next March, hopefully, fingers crossed. Many of you will know about the LSST, which is a telescope being built in Chile. It has recently been renamed, if you haven't seen, the Vera Rubin Observatory, after our famous female astronomer who showed dark matter existed in galaxies, so we're very excited about that. Decker French, who's speaking on March 23rd, will be talking all about this facility and the amazing things it's doing. And then, of course, we have our own giant Magellan telescope in Chile that we've been working on for quite a long time. I just thought I'd show you. I have a new animation. This is kind of fun, showing you this telescope. For those of you who haven't seen it, it's a really tremendous facility. It's 7 mirrors, about 25 feet across each. Effectively, it's an 80-foot mirror here. The dome is about 24 stories high. So this is a pretty incredible machine. And it's being built at Carnegie's Las Campanas Observatory in Chile. And this is the telescope that will be really good, for instance, for studying the atmospheres of those planets around other stars. Because you really need a big telescope to really do that properly. And there's some drivers coming down the mountain. We're making a lot of progress. I didn't have time to talk about it. We will at some point have to have a talk about this telescope. We hope this will be online sometime in the second half of the 2020s. And so with that, I'm going to end and say, we didn't really have a great debate, unfortunately, or so much in 2020. There's a lot more consensus, as I said, but there's still some really amazing questions, some of which I think could be answered in the next decade. If you were to ask me of the 4 things I talked about, what's the most likely, I would guess we'll understand fast radio bursts. The newest one seems to be the best to actually be answered, maybe. And hopefully we make some progress on dark matter and dark energy. And certainly the aliens, I don't know, that might take a little longer. Anyhow. But one thing I like to point out, and I'll end with this, that every time you build a new telescope, and I just showed you 3 of many new telescopes that will be coming online in the next decade, and you have a new capability, you discover new things you're not expecting. And so, in fact, if I come up here in 10 years and give this talk, most likely I'll have a list of all new mysteries in astronomy. And to me, this is one of the fascinating things about astronomy. You have to keep up. You have to keep coming to our lectures because it changes continuously. And so this is one of the exciting things about a field. It's a field that we write in real time, basically. And so with that, I'm going to end, and thank you for coming. And we'll take some questions. I forgot to mention that we actually have some microphones on the edges. We'd ask people to come up and use the microphones on the sides if you have a question, so that people at home, we do live stream our lectures, so we could, and we'll start here. Go ahead, sir.
Vera Rubin, 2 things. Vera Rubin, when she was here and gave a talk, several years ago before she died.
Yes, Vera Rubin did give a talk during this lecture series.
And she was asked about dark matter.
Yes.
She gave a very non-committal answer.
You said Vera Rubin was very non-committal, yeah.
She said, I don't know.
Yeah.
Second thing, you said that Shapley was at Santa Cruz. Now, Santa Cruz was only founded in '66, so was he the major factor in getting that program the prestige that it has now? Curtis was, did I say Shapley? I meant Curtis if I said Shapley. So Shapley was here
until 1920. In fact, when the debate happened in April, he was still here, but later that year he moved on to Harvard where he was the professor. And as many of you know, well, there's a fascinating story there. He and Edwin Hubble were not best friends, let's just say. And Shapley moved to Harvard to take that job. And in fact, if he had stayed here, he might have actually done what Hubble did and became much more famous. But Hubble had access to when Shapley moved to Harvard, he no longer had access to the telescopes at Mount Wilson. And Hubble did. And Hubble basically was able to solve this because he had access to Mount Wilson. Uh-oh. I know this guy.
Excellent. Just a quick question.
Sure.
So can we also look backwards to try to answer some of these questions, especially dark energy or dark matter, looking to see, was it a big bounce, was it a big bang, and is there things that we could look for that maybe could predate them, some type of matter that's left over that could answer some of these questions?
Oh, that's an interesting question. I don't know. I mean, we think that it's certainly, my guess is that if you imagine you had like an oscillating universe or something, that in the process of the crunch and then the Big Bang, you really kind of probably lost any memory of that. However, you are right about looking back in the sense that the real answer, particularly to the dark energy question, maybe less so with the dark matter, is actually understanding how dark energy has changed over time. So all the observations I showed you is mostly I'll call it recent, over 10 billion years or something. And so there's a lot of studies that are being done, that will be done in the next decade, to try to understand dark matter over the history of the universe. And that may provide clues as to which of the various scenarios for the dark energy it is. So those observations will be happening in the next decade. Yeah, yeah. Anybody else? Can you tell us about the image behind you, please? Sure. Oh, yes. For those of you who haven't seen it, this image is, in fact, it's probably better from the beginning, but I'll just keep it on this one. This is the Milky Way over our telescopes in Chile. So these are our current biggest telescopes at our Las Campanas facility. These are called the Magellan telescopes. What you'll see, you may be asking, well, why does the Milky Way not look that way from my backyard here in Pasadena? Is that what you're wondering? Two reasons. Well, the main reason, of course, is that the skies are very dark in Chile, which allows one to see these stars that you don't see. But the second thing is that the Milky Way never looks this spectacular from the northern hemisphere, because the southern hemisphere actually has a more spectacular sky. And I'm not just saying that because I run an observatory in Chile. Because the reason for this is the Milky Way galaxy, which is what you're seeing there, the center of the Milky Way is actually in the southern sky. And so from northern latitude, you never really see some of this bright part very well. But from South America, it goes right overhead. And so, in fact, the Milky Way is much more spectacular. I'll point out these little guys here. This is the Large Magellanic Cloud and the Small Magellanic Cloud. These are galaxies that are companions to the Milky Way that are falling into the Milky Way. And once again, those are in the very, very extreme southern sky. And they turn out to be very important for astronomy because they have different types of stars than we see in the Milky Way for the most part. And so all of these reasons, this is why a lot of astronomy is moving to the southern hemisphere. Anything else? Lots of mysteries and no questions? Sure.
What's the progress on the Giant Magellan?
Sure. The question is, what's the progress on the Giant Magellan telescope? So 5 mirrors are in process. 2 have been completed. 3, 4, and 5 are already in. Eventually, there's supposed to be 7, or potentially 8 if you want a spare mirror. The site has we've drilled the hole for the foundations already. It's a very impressive, very deep hole. And the mount contract, the contract for the part that actually holds the telescope, it's the most expensive part of that contract, has recently just been signed and shipped out. And so we have a company in Illinois that's actually making that mount for us. So progress is being made. We are still in the process of raising money for it. It's very expensive, and so that's a big portion of it. And our collaboration, for those of you who don't know, it's not just Carnegie. Carnegie is one of 11 institutions that are involved in that telescope, including the governments of South Korea, Australia, and Brazil. But it's making progress. Things are always much slower than you expect. For those of you who don't know, the Giant Magellan Telescope is, in fact, the headquarters is here about another mile or 2 east of here. And they have now over 100 people working on it, including many, many engineers. Yeah. Shelley.
How many scientists do you have at the Carnegie, and what's the breakdown between how many are men and how many are women?
Oh, that's an interesting question. I don't know if I know the complete statistics on that. We have, the question was asking about the actual Carnegie astronomers. I won't talk about, there are other components of Carnegie. I don't know enough about that to really answer. But in astronomy, we have about 15 individuals who are kind of more senior or tenured. We like to think we're tenured. We're not really tenured at Carnegie. But these are kind of lifelong appointments like myself. There's about 15 of us. And at the moment we added this, where are some of my postdocs? We had this number the other day. It's like 24, I think, postdocs. These are people who have just finished their PhD or in the last few years, and then they come and do further training and research at Carnegie. And what I'll say is that among that group, the diversity is actually very good. I mean, it's about at least 50% on average, I think, are women at the moment. But there's, of course, a slow drag because it takes time for that, how do I put this politely? For people to move on from their senior positions and be replaced by the younger folks. And so, because many of us I've been at Carnegie 25 years, and I'm not that old yet, so I'm not planning on leaving today. So what that means, of course, is that we've been slow to have that better diversity on the senior staff, but that's true across almost all of science. I'd say that astronomy, I think, does better than, for instance, physics or chemistry for sure. And it's a big issue in astronomy. I think we take diversity very seriously. What I will say is that while gender diversity at the PhD level is very good in astronomy, diversity for underrepresented groups, particularly Latinos or African Americans, is not quite there yet. We have a lot more work to do. So we have an undergraduate program that we do every summer. This is a good advertisement. If people have, if you're an undergraduate working anywhere in any of the Southern California colleges, we have an internship program where people come to Carnegie and work with us. And then we have a component of that project that we specifically target underrepresented groups. And this is a way to introduce people to astronomy careers much earlier, which I think is really one way you help solve that problem.
How many people do you have in Chile?
What's that? Oh yeah, well, then we have 75 people in Chile, so they're all mostly Chilean. Mostly, not all of them.
Thank you for being a wonderful communicator.
Oh, I appreciate it. Well, that's nice. I have to admit that this talk very much stressed me out because when I thought it was a great idea, and then when I went to sit down, I'm like, where are the debates? And I actually really think that there's something very fundamental there. It says something about the way the field works. I think when you work with teams of hundreds or sometimes thousands of people, the neutron star paper had 3,500 people on that one paper. I mean, it's hard to have very divergent views, I think, in that scheme. And maybe I'm wrong, or maybe we just know too much. But it's very easy for us as scientists to fall in line with the paradigms. And the question is, how do you think outside of the paradigm? I'm not going to stand up here and say I don't believe in dark matter. That would be very foolish, because I think the evidence, I've done a lot of papers on dark matter, is very good. But at some point you have to go, well, is there something we're missing? And it may be that scheme, the modern scheme, may not be as good at revealing that. So I don't know. Yeah. Is there a question way there?
Well, I'm just wondering from the science, has anybody combined the science with spiritual?
The question is science with spiritual. It's really interesting because I get a lot of requests for this all the time. In fact, I've talked with various people here about actually doing events where you brought together, for instance, religious individuals. You know, what does the church think, for instance, or various versions of the church think about astronomy and such. I'll point out that the current pope actually really is fine with the Big Bang and all this because he just thinks that, God started it all, and could be a great explanation. And so I think that in that scheme, it's interesting, but I don't know if there's a lot of people, astronomers themselves, that really dive so much into the spirituality component. I'd have to think about that. I don't know, are any of my other astronomers, I'm looking at them, I don't know, I'm seeing them shake their heads. What's that? Well, yeah, so the Vatican has a small number of astronomers who do, that's right, yeah. Yeah, I don't know. Yes, I'm not actually sure what they've done historically. That's a really interesting question. It would be interesting to know. Because, they did throw Galileo in jail 400 years ago. And so I would be a little concerned that they haven't always been so pro-science. Okay, one more question in the back there.
Well, just
Yes.
Don't believe.
Oh, interesting, yes.
It's not a belief, I mean, it's not religious, so I don't know, we're conflating.
It's an interesting question. I guess your comment is that I keep saying I believe. Well, I do believe, I guess, because the thing is we don't always, the thing about astronomy, people like to think that science is all about finding absolute answers, and it's not always absolute answers. The papers I wrote 25 years ago are definitely wrong, and now I know why they're wrong, because I've taken new observations, and I had limited access to information, right? And I think this is how science works. Edwin Hubble had limited access to information. And so I know now a lot more than Edwin Hubble could have, but that was just because of our timing. So to me, I don't like to think about this is definitely what occurs. And so I would say, and in the case of dark matter, since I can't point to it and say this is what the dark matter is, I have to leave it at believe. So yeah, that's interesting. I never thought about that. All righty, I think with that, we'll just wrap it up. Reminder, tickets for the 23rd of March become available tomorrow at 10 a.m. Thank you. We hope to see you all then.